To begin, we must first understand what black holes are. A black hole is a region in space where gravity is so strong that nothing, not even light, can escape. The boundary of a black hole is called the event horizon, and once anything crosses this boundary, it cannot escape. Black holes form when massive stars collapse under their own gravity at the end of their life cycles. When a star exhausts its nuclear fuel, it can no longer support its own weight, leading to a gravitational collapse. If the remaining mass is sufficient, typically more than 3 times the mass of our Sun, the collapse continues until a black hole is formed. There are different types of black holes, ranging from stellar mass black holes to supermassive black holes found at the centers of galaxies. Stellar mass black holes form from the remnants of massive stars, while supermassive black holes, which can have masses equivalent to billions of suns, are thought to form through the merging of smaller black holes and the accumulation of vast amounts of gas and dust over billions of years. Now that we have a basic understanding of black holes, let us consider the universe itself. The universe is vast, ever-expanding, and filled with galaxies, stars, planets, and various forms of matter and energy. The Big Bang theory is the leading explanation for the origin of the universe. According to this theory, the universe began as a singularity, a point of infinite density and temperature, and has been expanding ever since. This expansion is supported by the observation of the redshift of distant galaxies, a phenomenon where light from galaxies stretches to longer wavelengths as they move away from us. This observation, first made by Edwin Hubble in the 1920s, supports the idea that the universe is expanding from an initial explosive event. But what if our universe exists inside a black hole? This idea might seem bizarre, but some theories in physics suggest it could be possible. To explore this, we must delve into the concept of the multiverse. The multiverse hypothesis proposes that our universe is just one of many universes that exist. These universes, collectively known as the multiverse, could have different physical laws, constants, and even dimensions. One intriguing idea is that black holes in our universe might act as gateways to other universes. When a black hole forms, it creates a singularity, a point where density and gravity become infinite. Some physicists have suggested that the interior of a black hole could be another universe. This new universe would be separate from our own and exist within the black hole's event horizon. From the perspective of an observer inside this new universe, it would appear as a self-contained cosmos with its own physical laws. This idea can be linked to the concept of a white hole, which is the theoretical opposite of a black hole. While a black hole pulls in matter and light, a white hole would expel matter and light outward. Some cosmologists speculate that the Big Bang, which marked the beginning of our universe, could have been the event horizon of a white hole, where matter and energy from another universe emerged to form our own. This idea is rooted in theories of quantum gravity, which aim to reconcile general relativity with quantum mechanics. One such theory is the holographic principle, which suggests that the information contained within a volume of space can be represented as information on the boundary of that space. In the context of black holes, this implies that the information inside a black hole could be encoded on its event horizon. Physicist Lee Smolin proposed a related idea known as cosmic natural selection. According to this hypothesis, black holes give rise to new universes with slightly different physical constants. Universes that produce many black holes are more likely to create offspring universes, leading to a kind of natural selection on a cosmic scale. Another significant theoretical framework is string theory, which posits that the fundamental building blocks of the universe are one-dimensional strings rather than point-like particles. String theory allows for the existence of multiple dimensions beyond the familiar 3 dimensions of space and 1 of time. In some versions of string theory, black holes could act as gateways to these extra dimensions, potentially connecting our universe to others in the multiverse. Is there any observational evidence to support the idea that our universe could be inside a black hole? The short answer is no, at least not yet. This idea remains speculative and theoretical. However, certain observations in cosmology might be consistent with this hypothesis. For example, the cosmic microwave background radiation, the afterglow of the Big Bang, exhibits a pattern of fluctuations that some physicists suggest could be explained by the dynamics of a black hole interior. These fluctuations, mapped by satellites such as the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite, reveal tiny temperature variations that provide clues about the early conditions of the universe. Additionally, the accelerated expansion of the universe, attributed to dark energy, could hint at unknown gravitational effects related to black hole physics. Dark energy is thought to account for about 70% of the universe's total energy content, and its repulsive force counteracts gravity, causing the universe to expand at an accelerating rate. If our universe is inside a black hole, the properties of dark energy might be influenced by the black hole's gravitational field. Despite its intriguing nature, the idea that our universe is inside a black hole faces significant challenges and criticisms. One major challenge is the lack of direct evidence. While the theoretical framework might be sound, we currently have no way to test or observe the interior of a black hole directly. Another criticism is the complexity of the mathematics involved. The equations of general relativity and quantum mechanics are notoriously difficult to reconcile, and adding the concept of black hole interiors as new universes introduces another layer of complexity. The multiverse itself is also controversial. Some physicists argue that it is not a scientific hypothesis because it is not falsifiable. It cannot be tested or disproven with current technology. Others contend that multiverse theories can provide explanations for certain cosmological observations, even if we cannot directly observe other universes. If our universe is indeed inside a black hole, what would that mean for our understanding of reality? This idea would revolutionize our view of the universe, suggesting that our cosmos is just one of many, each with its own unique properties. It would also imply that black holes are not merely destructive forces but creative ones capable of giving birth to new universes. Future research in quantum gravity, cosmology, and black hole physics could shed more light on this hypothesis. Advanced telescopes like the James Webb Space Telescope and experiments in particle physics, such as those conducted at the Large Hadron Collider, might provide new insights into the nature of black holes and the structure of the universe. Theoretical developments, such as the study of black hole thermodynamics and quantum information, Stephen Hawking, will also play a crucial role in exploring within a black hole, is both mind-expanding and thought-provoking. While this idea remains entirely theoretical, it challenges our conventional understanding of space, time, and reality, encouraging us to think beyond traditional boundaries. As we continue to unravel the universe's mysteries, we may uncover extraordinary insights into the nature of existence. Time and space within a black hole. One of the fascinating aspects of this hypothesis is the implications it has for the nature of reality inside a black hole. According to general relativity, time behaves drastically differently near a black hole compared to our everyday experience. The immense gravitational forces near a singularity can cause time to stretch, slow down, or even appear to stop relative to an outside observer. This phenomenon raises profound questions about how events might unfold within the event horizon and whether our understanding of causality would fundamentally change in such a scenario. The spatial dimensions near a black hole singularity also undergo extreme distortions. The curvature of spacetime becomes so intense that it might lead to closed time-like curves, essentially time loops where time circles back on itself. While this concept is speculative, it underscores the necessity of a unified theory that reconciles gravity at cosmological scales with quantum mechanics inside black holes. Information and black holes. A cosmic paradox. Another avenue of exploration involves the role of information within black holes and its potential connection to the broader universe. The famous information paradox, popularized by Hawking, questions whether information that falls into a black hole is lost forever or somehow preserved on its event horizon. If our universe exists within a black hole, it could imply that the immense information in the observable universe is encoded or reflected on the black hole's boundaries. This ties into broader debates in theoretical physics about the preservation of information and its implications for fundamental laws like thermodynamics. Black holes as portals to other universes. The notion that black holes might act as gateways to other universes intersects with discussions about the multiverse. While the multiverse remains speculative, proponents argue that it provides a framework for explaining phenomena like the fine-tuning of physical constants and the unique properties of our universe. If black holes serve as portals to other realms, it could suggest a network of interconnected realities, each with distinct characteristics and evolutionary paths. This hypothesis also has the potential to unify disparate theories in physics. For instance, string theory posits that the universe's fundamental building blocks are one-dimensional strings vibrating in higher-dimensional spaces. These extra dimensions could serve as the structure through which black holes connect different universes or regions of our own universe across vast cosmic distances. Thermodynamics, gravitational waves, and observational advances. The study of black hole thermodynamics has revealed surprising parallels with the laws governing everyday phenomena. Black holes possess entropy, proportional to the area of their event horizons rather than their volume, hinting at a profound connection between macroscopic thermodynamic laws and the microscopic behavior of spacetime. Understanding how these principles operate within black holes could offer critical insights into time, information, and the formation of complex structures in the universe. Advancements in observational astronomy also play a crucial role. Observations of supermassive black holes at galaxy centers have uncovered phenomena such as accretion disks and powerful plasma jets extending millions of light-years. These discoveries confirm the existence of enormous black holes and their role in shaping galaxy formation and the distribution of matter on cosmic scales. Meanwhile, the detection of gravitational waves from black hole mergers, using instruments like LIGO and Virgo, has provided precise measurements of their properties, offering fresh insights into their dynamics. Future generations of gravitational wave detectors promise to refine our understanding further and possibly reveal new phenomena related to black hole formation and interaction with their surroundings. Philosophical and practical implications. On a philosophical level, the idea that our universe could exist within a black hole challenges traditional notions of cosmology and humanity's place in the cosmos. It suggests that the vastness of reality might be part of a larger interconnected structure, where black holes act as cosmic laboratories for creating and evolving universes. This perspective invites us to reconsider fundamental questions about existence, consciousness, and the nature of ultimate reality. Practically, this hypothesis underscores the importance of interdisciplinary research and collaboration across theoretical physics, observational astronomy, and experimental techniques. By integrating insights from various fields, researchers can push the boundaries of knowledge and explore new frontiers in understanding black holes and their implications for cosmology. Conclusion. While the notion that our universe might exist within a black hole remains speculative, it represents a captivating exploration of the fundamental nature of reality. By challenging conventional wisdom and expanding the limits of our understanding, this hypothesis inspires bold and creative thinking about the universe and our place within it. As we continue to investigate the mysteries of black holes, multiverses, and spacetime, we may uncover revolutionary insights that transform our perception of the cosmos and ourselves.